Alright, most towns use a water tower to store water and provide pressure in the pipes that'll deliver the water to customers. The figure below shows a spherical water tank that holds 5.8 times 10 to the 5th kilograms of water when full. Note that the tank is vented to the atmosphere at the top and that the pipe delivering water to the customer, customer Smith, is at a height of 4.7 meters above the level of the pipe delivering water to customer Jones. So they're at different elevations, and we want to find what's called the gauge pressure of the water at the faucet of each house when the tank is full. First thing to figure is that since this thing is vented at the top, we're going to have an atmospheric pressure at the top. It's in contact with the atmosphere. And atmospheric pressure would be 101,325 pascals. And we have this formula for how the pressure changes as a result of basically what's on top of it. So if you check out the depth of the water from the vent to the base here, we got to figure out what that depth is. Alright, so we'll call that the depth. And we could use the density of water to figure out what the radius of this tank is. So we'll call that R. So it's a sphere. And the volume of a sphere would be given by 4/3 pi r cubed. And we have the idea that there's a mass in the tank, and the mass would be given by the density of water times the volume. We know what the mass is. It's 5.8 times 10 to the 5th kilograms. Density of water is something we can look up easily. It'll be 1,000 kilograms per meter cubed. And then we could find the volume of the tank. Alright, so let me calculate that. Alright, we got 580 cubic meters of volume in that tank. We now want to set that 580 cubic meters equal to 4/3 pi r cubed and solve for r. This will reveal that the radius of the tank is 5.173 meters is the radius. So since we would have one copy of the radius there and another copy of the radius here, to get our depth we want 2r plus 18 meters. So that ends up being 28.34 meters for the depth. Then our change in pressure from the vent to the bottom would be given by rho GH, where rho is the density of water G is the gravitational field strength, and H will be the height of the column of water from the vent to the base. 277,700 pascals. Now the absolute pressure would be found by adding this to the atmospheric pressure. But it didn't actually ask for absolute pressure. It asked for what's called gauge pressure, which is just the difference between the atmospheric pressure and the water pressure for the house. So I would actually just leave it so like this is my answer for the Jones house. When it comes to the Smith house, though, they're not as far down in elevation, so we have to take that into account, that this H is 4.75 meters higher than the Jones house, so it's going to be less pressure at their house. So to figure that out, I'll do another one. Delta P for Smith would only be rho times G times 28.34 meters minus 4.75 meters. I'm basically trying to get the distance from the vent down to the elevation of where the water is going to come out in the Smith house. So I would do 1,000 kilograms per meter cubed, 9.8 newtons per kilogram, and 23.59 meters there for the depth. Looks like about 231,100 pascals. That'll do it.